minute. There we go. Good morning, everybody. How we doing?
Good morning.
Good morning. Good morning. Let's see here. So I have managed to cram the first 5 chapters, 0 through 4, into the midterm scheduled on October 1st. And let me just show you some of the details for that. Show you the, here we are on the 17th. I changed our homework 2 due date to Friday at 11 p.m. The chapter 3 homework is due on the 23rd. We'll actually finish chapter 3 today and start chapter 4. And then the chapter 4 homework will be due 1 week after that at 11 p.m. the night before the midterm on October 1st. So it's there'll probably be like five conventional pages, 1 for each chapter, maybe 2 or 3 questions per page. So 5 times 3 is about 15 or so questions. So that's more or less what we're looking at for the midterm here. And we'll see, that leaves us half the lecture today, and then Tuesday, Thursday, and Tuesday to do chapter 4. And that should be plenty of time to do that. So, and I won't go on to chapter 5 until we're done with chapter 4. And anyway, I won't go on to chapter 5 until we've had the midterm. So I'll review a little bit before the midterm, but that's the timing on things right now. A little more congested than I had hoped the week of the midterm, but hopefully you can get everything completed by that time. And if the homeworks are too extensive, please let me know, and I can also look at the amount of homework that's being assigned. I'll take a review of that for chapter 4, for example. And the midterm, good morning. The midterm questions will be from the homework. Yes. So.
I would say lengthwise, yes. It's pretty long. I don't know about other guys, but lengthwise it was like really time consuming, or like it takes like long time. You know what I mean?
Okay.
That's the only thing.
Yeah, it's really hefty.
Yep.
Okay. All right. Okay. So I tell you what I can do. I don't think anybody's done chapter 4. So like what we're looking at here is I actually cannot show the individual grades reports here. So hold on, let me check this out off screen here. So I want to see how many folks have started. There's a couple of folks have finished chapter 3. So I'll be able to cut down the workload on chapter 4. I'll select I'll select from chapter 4. Yeah, sorry, chapter 3 is already sort of,
I know.
sort of gone. Sorry.
Thank you.
Okay, all righty. But I mean, it's good practice. I mean, I know it takes a long time, but I will cut them down forward probably. Yeah, and so, all righty. Let us see here now. Let's go to, let's go here, yeah. So, okay, so here's where we are in the, whoops, it's gonna stay up there. In the process of understanding uncertainty propagation. So just to review again, most of the operations that we do in chemistry are addition, subtraction, multiplication, division, or exponentiation and logarithm. So a logarithm is the inverse of an exponentiation function. So here, if we have a function y equals x to the a, the uncertainty in y is a times the uncertainty in x, right? So this does not actually deal with the uncertainty in a, but it does deal with the uncertainty in x, right? So, for example, if you have an exponent of 1/2 and a relative uncertainty of 2% in x, then the relative uncertainty in y will be 1/2 of that value because the exponent is 1/2. So that will be down around 1%. On the other hand, if you have y equals x squared and a 3% uncertainty in x, then the uncertainty in y will be 2 times the uncertainty in x, right? So this is assuming exact exponents, right? And only the uncertainty in x, which is pretty much always the case in chemistry here, right? So for an example of that, we could take an object falling and the distance that it falls is equal to 1/2 gt squared, where g is the force due to acceleration due to gravity, and then this is a solution to a differential equation. And so we have 1/2 is exact, g is exact, t is the time, which is measured normally, and 2 is the exponent, right? So if the object falls for 2.34 seconds, then the distance is 1/2 times 9.81 meters per second squared. That's 2.34 seconds squared equals 26 meters, right? Now, if the relative uncertainty in time is 1%, what is the relative uncertainty in distance? And so the function that we're using is 1/2 gt squared. That gives us a relative error in distance of 2 times the error in time. So 2 times 1% is 2%. It's a little bit onerous when you look at it at first, but if you work in relative percents, it's pretty straightforward. So now there's a common mistake is to think of writing 1/2 gt squared as 1/2 g times t times t. Now, this is algebraically correct, but for the purpose of uncertainty propagation, the t values are what we describe as coupled. So now this is the most obvious case of coupling because it's t times itself, right? And so whenever t fluctuates up, both of these terms fluctuate up. And whenever t fluctuates down, both of these terms fluctuate down. So uh, that is why the fluctuation in the distance is twice the fluctuation in time, basically, because these two time variables are coupled. So if we talk about percent error in distance, that's twice the percent error in time, because we have t times t, and they're both high by the same amount, or low by the same amount, or right by the same amount, if you can say that. So so let's do an example. If the height has an uncertainty in 1%, what is the uncertainty in time? Well, let's see here. Let's do this one. Oops. So what we have is, sorry, I gotta adjust myself here. We have a case where the height h is equal to 1/2 times g times t squared, right? And so the error in h will be a function of the error in t. Right? It will be a function of the error in t. And so hold on just a second. I think I'm in the wrong one. What's the uncertainty of time? Okay, so this is where we're actually doing this backwards, right? So now if we want the uncertainty in time, time as a function of height, then what we need to do is we'll solve for t, right? And so t will equal 2h over g, right? T squared will equal that, and then t will equal the square root of 2 over g times h to the 1/2. So 1/2 and square root are the same. I'm just, for idiosyncratic reasons, I'm just separating them like this. So in this case, the percent error in t is equal to 1/2 the percent error in h. So if the so now if the percent error in h is equal to 1%, then percent error in t will equal 1/2 times 1% will equal 0.5%. So it's fairly straightforward. This is just, there's just one twist, and this is that we have to solve first for time. solve for T to do the error propagation, right? So now the other place where this type of thing comes up is in pH problems. So I'll publish these notes in case I'm going too fast today. And yeah, I will have a review before the midterm. But, so if we consider the function pH is equal to minus log of H plus, right? That's a, typical chemistry function, right? That's how we actually define pH. We just make this scale where we take the negative log of H plus so we can compare huge magnitudes of hydrogen ion concentrations with a single number, right? There's no exponents in pH normally, right? So now if the pH is 5.21 plus or minus 0.03, right? That's the kicker there. Find H plus and its uncertainty. Let's say E H plus, right? We'll try to, oops, yeah. I won't try to superscript that right now. But so this is actually real reasonable because pH meters, these little electrochemical jobbers that you use where you stick the probe into the solution and it reads out the pH. These are electrochemical and they actually read in this logarithmic domain. So there's an electrochemical phenomenon that happens at the pH probe that converts the H plus concentration into a potential that's proportional to its logarithm. So this is a very reasonable problem. Let's see what Harris has to say this, right? So so let's see here. So we want we have pH and we want to find H plus, right? So we have to solve for H plus the formula pH equals minus log of H plus, right? And the way to do that is simply take the reciprocal function here, H plus equals 10 to the minus pH, right? So it's 10 to the minus pH is 10 to the minus 5.21 plus minus 0.03, right? So in this case, for y equals 10 to the x, then EY divided by y is 2.306. It's kind of stupid to have 4 6 things here. It's 2.3 times e to the x, right? So the error in x is 0.03. Therefore, the relative error in y, EY over y, is EH plus over H plus, is 2.306 times the error in pH. So that's 2.30, 2.3 times 0.03, and this 0.03 is from up here. That's the 0.03 that's coming in down here, right? I can't edit that, unfortunately. Yeah, that's 0.0691, right? 2.3 times 0.03 is 0.06. So that's how we do that type of problem. And then we'll work one out on paper again, right? Now, if you measure uncertainty in H plus, if you make a measurement where you know the uncertainty in H plus, right? So this is EH plus, right? EH plus. I'll put a dot there to indicate subscript, right? EH plus is 0.0691. That's 3 sig figs on an uncertainty. Okay, that never happens, but let's just say it's 0.069, right? So then H plus is 10 to the minus pH is equal to 6.17 times 10 to the minus 6 molar, right? This is all let's see, this is the relative uncertainty in H plus, right? This is H plus over its value is 0.069, right? Then the error in H plus, the absolute error in H plus is 4.3 times 10 to the minus 7. So what we did was we started up here. We had pH with an uncertainty in the pH, right? Then we found that the relative error in H plus was 0.06. Then the relative error, this is actually percent error. We'll call it relative error. Is 0.069. So then we know that the error in H plus divided by H plus is 0.069. We know the pH is 5.21. So just put this on a new line here. So this is how we find H plus, right? H plus is equal to this value, right? So we go from relative error and its magnitude to the magnitude of the error. So this is the relative error. That's 0.619, 0.069. This is the magnitude of the answer. So the error in H plus divided by the answer is equal to this. Therefore, the error in H plus is 4.3 times 10 to the minus 7 molar. So now we can state the uncertainty. Actually, let's do it like this. We're going to drop the second digit in the uncertainty. Let's say that it is 6.2 plus minus 0.4 times 10 to the minus 6 molar. That is H plus, right? That is concentration. We'll put that guy in square brackets there.
Hey, Professor.
Yes.
I just have a quick question. On that 6.1, that subscript of 7, I'm just curious, how would you punch that into a calculator?
This 6.17 times 10 minus 6.
Mm-hmm.
Okay, so for that's called exponential notation, and in many calculators, it shows up as like you put in the mantissa, right? You'd say 6.17, then you hit EEX, and then say 6 and change the sign of 6, right? So it's a little bit tricky. Let me see if I can show you. I'll show you on a couple calculators here if I can do it on my phone here.
Dr. Terrell, I think he's talking about the subscript. I think that's not a subscript. That's just a error. 7 should be 6.17. That's not a subscript 7, right?
Well,
that's
is that what you mean? The uncertainty in this digit here?
Correct. Yeah, the 7 subscript.
Oh, I see. You don't need to deal with it. You just enter 6.17 to do a calculation, right?
Yeah.
So what is indicated by the subscript is the fact that it has uncertainty, that's an uncertain digit.
Okay, now I understand. Thank you.
Okay, cool. Excellent. Good. I notice that when I say okay, cool, my phone thinks I'm saying okay, Google. No, I did not want you, Google. I did not want you. No, I did not want you, Google. I did not want you.
Sorry, I don't understand.
I love it. Okay. So this is how to get from, this is a long process. So let me see if I can maybe pare this down just a little bit for y'all. Okay. So let me try to pare this down here. What we have is as follows. We've got pH equals 5.21 plus or minus 0.003. So this is this is the uncertainty. This comes from an electrical reading on a meter. Right? And so then H plus concentration is equal to 10 to the minus 5.21 . Oh, I'm sorry. There's only 1 0 there. Sorry about that. 5.21 plus minus 0.03, right? And so H plus equals 6.1660 times 10 to the minus 6, right? So this is a carrying insignificant digits, right? Because I think there's actually only 2 sig figs, this value. And then there's 5 sig figs here, so that's sort of exaggerated, right? But it's okay because we're just calculating, right? I always say the EH plus is equal to over H plus is equal to 2.3 times E and pH. And so now if we just start substituting in here, the air in the H plus is equal to H plus times 2.3 times air in pH. And that's equal in turn to 6.166 times 10 to the minus 6 times 2.3 times the air in pH, which is 0.03, right? And so this comes out to 0.43 times 10 to the minus 6. Right? It's the air and the H plus concentration. Is 0.43 times 10 to the minus 6. And now these units are now molar, right? So what we're going to say here is that the H plus ion concentration is equal to 6.1 plus or minus 0.4 times 10 to the minus 6. So let me ask real quick, how many sig figs are in this answer?
2.
Exactly right. 2 sig figs. 1, 2. Right? And this is the uncertainty, right? And the uncertainty is 1 sig fig. So there are 2 sig figs. Perfect. Excelente. So let's go back to the little point here. And so we can do this one at some point. It's a straightforward transformation. I'll do this one and I'll post it. But there's other rules, right? This is a summary of them. We have plus and minus are the same. We have multiply and divide are the same. We have exponentiation and logarithms, right? And typically, actually, we could run into this one or this one. Yeah, we could probably run into any of these 5. And these are all basically derived from the same place, right? So there's no error in A here, right? And there's no error in the value E here, right? It's just comparing errors in X and Y. Okay. So these are more formulas that you can use. So now the next subject here is properties of uncertainty for systematic error, right? And this is different because what we've been doing so far is random error, which oscillates between positive and negative. And now we're going to do systematic error, right? So systematic error it's a funny thing to propagate, right? Because you can always calibrate to remove systematic error. I mean, normally you can, right? Let's say that you haven't calibrated a pipette or something, and in that case, you can use this approach to just to estimate the total error for even using an uncalibrated system, so long as you know what the magnitude of the systematic error might be, right? So one such case is to take if you have a volumetric pipette, right? And that pipette, you know that it delivers 25 mils plus minus 0.03. This is what makes it class A, right? That it has this amount of uncertainty in milliliters. So that means that if you use it properly, it will give between 24.97 and 25.03 milliliters. It's actually quite accurate and quite precise, right? But there is some systematic error here. And that is what's meant by this range, is that this range is actually part of a systematic error, right? So you can calibrate this thing and figure out that it delivers exactly 24.991 plus minus 0.006, right? So this is a factor of 5 smaller than 0.03, right? This is once you calibrate it, right? However, if you don't calibrate it, you have only and let's say you kerchunk into something 4 times with it, then what you'll get is 0.12 mLs of uncertainty, which is 4, right, times 0.03. So 0.12 here is 0.03 times 4 is 0.12. Okay, now if you calibrate it and you do it 4 times, then what you're going to get is 0.012, right? It will be the uncertainty in that answer, right? Let me turn this guy here. Right? So 0.012, this guy comes from this. So if you have 0.06 squared plus 0.016 squared plus 0.01, or if you got this 4 times squared, right? Then you've got 4 times this value squared, square root of all that, right? Here, I'll do this on the stupid thingamajinger. So, let me get this straight. I'll go for the whole banana here. Let's say 25.00 plus minus 0.03 times 4 is 100 plus minus 0.12. And 24.991 plus or minus 0.006 times 4 is 99.964 plus or minus 0.12. Okay, hold on, I'm gonna put this over here. So now this is what it boils down to. This is systematic, and this is random. Right? Because this is a calibrated version. Version of this guy up here. So in this case, the systematic we measure 4 times. And the error accumulates 4 times. Right? So this is 25.00 plus minus 0.03, oops, times 4 equals 100.00 plus or minus 4 times 0.3 is 0.12 mLs. This is systematic error propagation. Right? Random error propagation will be, in this case, 24.991 plus or minus 0.006 mLs, right? Times 4 equals 24.991 times 4 is equal to 99.964. Right? Plus or minus the square root of 0.006 squared plus 0.006 squared plus 0.006 squared plus 0.006 squared. Right? These are the 4. This is the first aliquot, second, third, and fourth aliquot that we took. Right? So this is equal to 99.964 plus or minus the square root of 4 times 0.006, which is equal to the square root of 4 times the square root of 0.006 squared, sorry. So that's 99.964 plus or minus square root of 4 is 2 times square root of 0.006 squared, which is equal to 2, oops, sorry, I've got to move the paper up here, 99.964 plus or minus 2 times 0.006, which is equal to 99.964 plus or minus 0.012. Right? 2 from 6 is 12. Let's see here. So the 2.3 is a constant. 2.3 is a constant when we're doing logs, yes. That's means that e to the x is 2.3 times, wait, no. Natural log of x is 2.3 times base 10 log of x, is where that comes from. That's 2.3. And then shouldn't the random one have 0.0024? And 6 times 4 is 24, right? But when we add them root sum square like this, then it comes out to be a smaller value, 0.012. Because it's basically, you do it 4 times, so you get the square root of 4 times the uncertainty in each one, right? So that's 2 times the uncertainty in each one. So I don't know how else to say that. It's just sort of like kind of how it works out there, right? So let's see. Going back to how. Now, oh yeah, and so there's just like, I would say, just park your brains for a second and let's talk about this, because this is not on any exams. This is not on, but it's just an interesting sort of a story about systematic and random error in atomic masses, right? So it turns out that most atomic masses in the periodic table have a variation in them, which is actually a systematic variation. So, for example, if you take oxygen, it's 15.999, and it's about plus or minus 0.00074, right? So it's 0.03 to this. So that's the interval, is 15.999 plus or minus 0.74, right? Or it's the average of these plus or minus 0.74, something like that, right? But this range comes from isotopic variation, right? And if you sample oxygen only from the air, you get oxygen, let me see, oxygen 16 plus a specific mole fraction of oxygen 18, and that gives you 15.9994 exactly as the atomic mass, average atomic mass of oxygen in air, right? But if you sample oxygen from water, it has much less O18, but there's a wide variety of O18, right? So depending on where you get the water from, etc., the amount of O18 can vary a lot, and therefore the atomic mass varies a lot. Right? If you take it from carbon dioxide in the air, it varies. Carbonates, then N2O, God knows why that's wide. Then nitrates, oxides, and plants and animals, right? So all these different sources have different amounts of O18 in them, right? And they vary from a very low from oxygen, some water, to a very high from some probably recently formed atmospheric process. God knows why N2O is enriched in O18. I do not know. But if you, you'll never have to do this, I promise, ever, unless you work for NIST or a mass spec group, perhaps. You don't have to worry about this isotopic variation for most elements, right? because oxygen, we already have 5 sig figs, right? 15.999 is really, really precise for the molecular mass of oxygen. But the uncertainty that it is reported with in the periodic table is actually a systematic uncertainty, right? So that all of the uncertainty in, like if you have, I don't know, I can't think of a good example, but it's a systematic uncertainty. And the actual uncertainty depends on, or the random uncertainty depends on the origin of the water, of the oxygen, whether it comes from water, CO2, or atmospheric O2. So it's kind of a weird thing. I think I've burned my 50 minutes today, but this is the end of chapter 3. And next time we're going to start chapter 4. And I will go ahead and I'm going to cut down the work in the chapter 4 homework for you. I'll go ahead and do that right now. And I'll post these notes that I've made for today. Are there any questions? Does anybody want to murder me now? And they're willing to say it. You can use a pseudonym.
I just wanted to say thank you for producing the homework. It's a big help.
Okay, I'm sorry. I'm sorry I haven't done it up to now. But
Not at all.
Don't murder me. Don't murder me. So I will reduce it in chapter 4. Okay, guys. I'll talk to you soon. I'll see you on Thursday, and we'll do chapter 4.
Thank you, Dr. Taylor. Have a good one.
Thank you, guys. Thank you so much. Bye-bye.
Thank you,
Bye-bye.
Professor.
Yay. Okie dokie.